This is a titration of a weak acid. We know it's a weak acid because we're given a Ka value, and we're going to represent it as HA and its conjugate base as A minus. And we're going to be using a strong base to titrate this weak acid. So the initial question is calculate the pH at the start. So what we have in the beaker is a weak acid. So this is a weak acid problem. And we react the weak acid and water. So we generate some hydronium ion and the conjugate base. We initially have 0.1 molar. Assume we don't have any of these to start. We're going to lose a little bit of the weak acid, gain that much of H3O plus and A minus. 0.1 minus X, X, and X, because equilibrium is the initial plus the change. We write our equilibrium constant expression. And we're given our value of Ka as 1.3 times 10 to the minus 5. Okay, so we're going to solve this by, we'll pop in our values from the equilibrium table, or the ice table, and we can solve this by method of successive approximations. We'll solve for the highest power of x, x squared, and we see x squared is going to be equal to Ka times 0.1 minus x. Now what we really want is not x squared, but x, so we can take the square root of each side. Start with the first approximation of x sub 0 is equaling 0. And we put in 0 in for this x, multiply it by Ka, take the square root, and we find that x sub 1 is going to be equal to 1.14 times 10 to the minus 3. Then we take this value of x, plug it in to the equation here, calculate out a new value to see if there is any difference, and there is not, at least not within sig figs. So we're done. We know what x is, and since x is equal to the hydronium ion concentration according to our equilibrium table, we can calculate pH. And that's equal to 2.947. With 2 sig figs, our pH is 2.95. Alright, so now we want the pH of the solution after 20 milliliters of our base have been added. So we need to know how much of our acid was initially present and how much was consumed. So we started with 40 milliliters. Of 0.1 molar solution. And again, we know that molarity in moles per liter is the same as the concentration in millimoles per milliliter. So 0.10 millimoles per milliliter multiplied by our initial 40 milliliters means that we have 4 millimoles of HA at the start. And we've added 20 milliliters of our base. So we've added 2.0 millimoles of our base. So what this means is that our strong base has converted 2 millimoles of HA to A minus. Okay, the conjugate base. Okay, because we have HA, when it reacts with a strong base, is going to go to A minus plus water. So 2 millimoles of our HA converted to A minus, and therefore we have 4 minus 2 millimoles of A minus remaining. So we have 2 millimoles of HA left, and we have 2 millimoles of A minus. This is a balanced buffer. Meaning our concentration of our acid is the same as the conjugate base. And we are also exactly halfway to equivalence. So halfway to equivalence, meaning we have a balanced buffer. We know that pH is equal to pKa. And this is equal to the negative log of our Ka. And that's equal to 4.886. Okay, 4.87. Okay, just to be sure, I kind of skipped over this. The reason pH is equal to pKa at this point is because if you look at the Henderson-Hasselbalch, you have pH is equal to pKa plus, I can't get it. Let's try this. pH is equal to pKa plus log of our base to our acid. And this whole thing goes to 0 because we have log of 1, because the base is equal to the acid, and the log of 1 is equal to 0. So we're left with pH is equal to pKa. Okay, next point on the curve. Addition of 30 milliliters of sodium hydroxide, which means that our added hydroxide is millimoles. Okay, so we started with 4 millimoles of the HA, and at this point 3 millimoles of HA has been converted to A minus. And since we started with 4 millimoles, we have 1 millimole of HA left. Alright, so we've added 3 millimoles of hydroxide. That means 3 of our 4 millimoles of HA have been converted to A minus. So we have 3 millimoles of A minus. We have 1 millimole of HA that's left. So when we apply Henderson-Hasselbalch, we have pH as pKa plus log of our base to our acid, because what we have is a buffer. Our base is 3 millimoles, and our acid is 1 millimole. Okay, remember that we have both of these items in the same beaker, so the ratio of the moles is the same as the ratio of the concentrations. We can save ourselves some calculations there. And when we chunk this out, our pKa is 4.886 plus this is 0.477, and our pH at this point is 5.363. Well, with 2 sig figs, it's 5.36. Okay, the next point is we have 40 milliliters of sodium hydroxide, which means we're going to be at the equivalence because we're going to get 4 millimoles of hydroxide. I'll show you that. So all of our HA has been converted to A minus. So what do we have in the beaker? We have simply A minus. This becomes a weak base problem. Okay, the concentration of our weak base is we have 4 millimoles. And our initial concentration is 40 plus 40, or 80 milliliters. Remember, millimoles per milliliter is the same as moles per liter. So our concentration of our weak base is 0.050. Okay, our concentration's been cut. Alright, so we have our concentration of our weak base. We can write out our ice table. Our weak base reacting with water to reform a tiny bit of our conjugate acid and hydroxide. So initial change equilibrium 0.05. We're going to lose a little bit of that. Assume we don't have any of this to start. Equilibrium concentrations being the initial plus the change, and our Kb is now equal to x squared over 0.05 minus x. Okay, now Kb is the Kb of our conjugate base. So Kb is equal to Kw divided by Ka. 1 times 10 to the minus 14 divided by our Ka of our initial acid. And we find our Kb is 8.7, no wait, our Kb is, that's not it, 7.69 times 10 to the minus 10. Okay, so we can rearrange our equation here to solve for x. X is going to be equal to the square root of x squared, which is going to be Kb times 0.05 minus x to 1/2. Again, x sub 0 is equal to 0. We find x sub 1 is going to be equal to 6.2 0 times 10 to the minus 4. There's no change in x sub 2. So we're done. This is our hydroxide ion concentration. We can calculate our pOH, and our pOH is 5.208, so our pH is 14 minus our pOH, 8.792, or 8.79. Okay. And finally, the pH of the solution after the addition of 50 milliliters of our hydroxide. We can find our added hydroxide moles. 0.10 millimoles per milliliter times 50 milliliters. We now have 5 millimoles of added hydroxide, and 4 millimoles were consumed in converting the HA to A minus. So we have 1.0 millimole of excess hydroxide in 90 milliliters, because we have the 40 plus 50. And this is a strong base calculation. So our pOH is equal to our millimoles of excess base, 0.1 or 1.0, millimoles in 90 milliliters, because that's 40 plus 50, and our pOH is equal to 1.954, and our pH finally is 12.046 or 12.05. Okay, one point before I cut off here. I do recognize that there is A minus here in solution. We have 4 millimoles of A minus in solution. However, its contribution to pH is going to be very tiny compared to this strong base that's in solution. So while this is going to make the solution slightly basic, its effect is swamped out by the presence of this strong base.